Good morning and welcome back to this course on advanced computer algebra. This is the 10th lecture, and today we will mainly talk about applications of lattice reduction. Last video I showed you what lattice reduction is and how to do it with the LLL algorithm in polynomial time. So let's quickly remind ourselves what the setting is. We had some vectors given. Maybe they were, let's say, the integers with n components. And then what we considered was the integer module generated by them. So maybe I will write it today like this, which is a notation that is supposed to refer to the set of all linear combinations of the b's with with integer coefficients. So all the alpha 1 b1 plus 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 alpha m bm, where the alphas run through the integers. So that's a certain subset of set to the n, and such as a subset is called a lattice. And the b's are called a basis of the lattice, and the question we were dealing with was how can we find short elements of the lattice? And this is a difficult problem for which there's no efficient algorithm is known. But we had the LLL algorithm that solves this problem somehow with a little bit of a concession. And the concession was that the LLL algorithm returns not necessarily the shortest vector, but it returns a vector which provably is not much longer than the shortest vector. And not much longer than the shortest vector means that it's off by at most a certain constant, and the constant you can quantify, and it depends only on the n and otherwise not on the lattice. So if we now turn to the question of applications of this algorithm and this technology, then there's a guiding principle, and it is that you want to solve a certain problem, so you have some information given, and you want some information that is derived from it. And you can phrase a number of problems in terms of lattice reduction by coming up with a lattice that in which the things that you know are long vectors and the things that you want to know are small vectors. And then you do LLL and it solves your problem. So the question of finding a short vector is not it's not somehow a question of original interest. It is a question of secondary interest, and it's interesting because many other problems of primary interest can be translated into a lattice reduction problem. So it's a little bit like with Gröbner bases. When if you know about Gröbner bases, then usually you would not the necessity to compute a Gröbner basis doesn't come out of the blue. But what happens is that you have questions about polynomial ideals that naturally arise, and you can translate many of them into a computational problem for Gröbner bases, and that's why Gröbner bases are interesting. So it's the same here. A lattice reduction is interesting because many other things can be rephrased as lattice reduction problems. So let me give you an example. Actually, let me give you many examples. The first example is a Diophantine approximation. What is this? This you can also say this is rounding backwards. So if you have a third, this is a rational number. You can't exactly express it in a decimal expansion, but you can approximately express it. You can say this is 0.3333, and at some point you have to stop, and then whatever comes after you don't know. And it's you know how to get from here to there. And the funny thing that you can do with LLL, and that seems very magical if you see it for the first time, is you can go backwards. You can say, given this, I want to know what was the rational number that produced this approximation. How is this possible? It seems that this is an illegal question to ask, because here you have thrown away information. The information here is gone. You don't know how this continues. So without having this information, how could you possibly get back to this exact rational number? And the answer is we're taking an additional aspect of it into account, and what we do here is not restoring, it's not really restoring this discarded information, but what we do is we consider this here as an exact number. So what is it? It could be this here. So, and we are asking ourselves, is there a rational number that is very close to this number but has a shorter numerator and a denominator? Short. This is the keyword for LLL. So here's how you do how you solve this problem with LLL. So let's see, what do we want? So we have, let's say this is x. This is the true number, and let's say this is xi here. This is the approximation. So what we have is x minus xi is equal to epsilon, and this is small. And let's say the x is p over q, and p over q is what I want to know. So this is p over q minus xi is equal to epsilon. And now multiply by q, so we get p minus q epsilon equal to q xi is q epsilon. And then write a 1 here to make it explicit what we have. So we have the 1 and we have the xi, and we want to get the p and we want to get the q. And here we don't really care about this, but this is a small, so this is a rounding error. Okay, so let's see how we can do this. So we could set up a lattice that is like this. So I want to get a lattice that so is generated by certain things and is such that it contains this PQ vector. And then maybe here something in addition that amounts to this round off error. So I could say we take 1 and minus xi. And then it's a little bit like when you invert a matrix, and you would say, okay, if I take here 1, 0, and here I take 0, 1, then p times this vector plus q times this vector, that would be exactly q times epsilon. So if I get q times epsilon here, then this is small. However, I need the whole vector to be small. I want this to be small. So all together, but for p and q I don't really have a control how this could be small. They just are what they are, but I have some degree of freedom here, so we want these to be long. But there's nothing I can change about them. They are given. So I'm given the xi. I cannot change the xi. Actually, I can change it because I care about this equation, this equality, and this equality is not changed if I multiply it by something non-zero. So let's multiply it by a w, a weight, a positive number, and that would introduce the w here and here. And then these, if you think of a big number, then this would be long vectors as we want. And here I'm not destroying anything, because here the w gets also multiplied, but W Q epsilon, this is, well, is this big or is this small? The epsilon is small, the W is big, so let's say this is normal in size. If you consider W as roughly 1 over epsilon, then they will cancel each other. So this has this first component has a size that's the same as P and Q. So they are, again, they are what they are. In order to have this a small vector, I just have to make sure that I can choose the W bigger, so that these vectors here are bigger than this. And then LLL should, if I feed this into LLL, this here should come out. So let's see if this works in reality. Here's a Mathematica session, and maybe let's not take 1/3, that's too boring. Let's take 17 over 29. Let's round it. That's the easy part. Here we go. So then what did we say? We said we take 1 and this funny number here, xi, and we take it to a high power. Maybe here 10 to the 6 would be enough. And then maybe we prefer to work over the integers. So let's round this to integers. And then I attach an identity matrix. Of size 2 to it, and then transpose, because we think in columns, but Mathematica thinks in rows. So here is the basis of the known things, and you see that these are long vectors because they contain long numbers. So if I look at the norm of these vectors, you see, oh, okay, that's 10 to the 6, something in this range. But now if you apply lattice reduction, lattice reduce 3, then you see, oh yeah, I forgot the minus, never mind. Then you see here's the P and here's the Q. And here, what is this? Well, this is the 10 to the minus 6, which is the error here, times the 10 to the 6, which is the W. So that balances somehow out, and then the 3 is a rounding effect. And you see here another vector. Well, that means that well, this you get a basis, so you get two vectors, but this vector is much longer than this one, and so you don't expect it to have any meaning. But what you will look for is a situation like here, where the where one vector is much shorter than the other ones, and then that doesn't prove anything. But it gives you a hint and a strong suggestion, a strong indication that what you have found is not accidental. Okay, so let's play this game with a more interesting expression, or a more interesting rational function. Let's take maybe this one. And see if we can recover this too. And you see, no, it doesn't. It doesn't reproduce the number that we started with. It finds something better. So here is a fraction. The quotient of these two numbers is also close to this, and for the same amount of digits. So let's look. Yeah, you can't distinguish this. It's, yeah, well, you can distinguish it in the last digit. You see a difference, but LLL thinks that this is the number you started with because we didn't provide enough accuracy. So in order to really get the result, yeah, you can estimate this by counting digits. You can say these are 6 digits altogether, but here you have 8 digits. So this true fraction contains more information than this approximation. So here you really have the problem that you cannot you cannot recover the information that was discarded in this rounding. So what LLL does seems magical, but it can't do real magic. So if we want to recover this, then we need to approximate this to a better accuracy, maybe to 20 digits. That would be more than enough. Let's see if this is enough. So this is a higher epsilon, but the epsilon will not take any effect if I don't also scale up the W. So let's do this. Maybe take also 20 digits. And then here you see it works. Here we get the thing that we entered, except for the sign which I should have put into this thing. And what happens if we take a number that is not a rational number? Well, then we get a rational approximation. So for example, if we do this with pi, then we get here a fraction. This is a rational number that is very close to pi. So let's see what the difference is. Right. Maybe to 50 digits. Or you see, so this is 20-digit accuracy. So here that's because we have put here the W to 10 to the 20. Yeah, somehow what LLL does is it takes this standard approximation that is encoded by the floating point approximation. So if you take pi 20 digits, then this is also an approximation, a rational approximation somehow, because that's 10 to the 20 round by 10 to the 20. So this is this fraction. But here all the information is in the numerator. And since all the information is in the numerator, you need a very long numerator that has as many digits as you have information to provide. And the denominator doesn't know anything except of how big it is, but it doesn't know any details. What LLL does is it distributes equally, roughly, the information that is here only in the numerator, and it distributes it between numerator and denominator. So that's why here you have roughly 10 digits here and roughly 10 digits here. Okay. And with this result and the lemmas that we had in the previous lectures, you can also make now a statement of the form: if pi is a rational number, or if pi were, we know it's not, but if pi were a rational number, then its denominator or its numerator would have to be at least so and so big, because if it were smaller, then LLL would have found it, but it did find this. And so that gives a bound on how big the components of a fractional representation of pi have to be at least. So this is used in experimental mathematics, where you have quantities like pi, but maybe a bit more weird, defined by converging sums, infinite series, where you get some numbers that you don't know where they are, and then you ask yourself, is this rational? Or maybe you ask yourself, is this related to some other numbers that I know? So that would be the second application, just a generalization of Diophantine approximation. It's called integer relations. So the task is here, given approximations, let's call them xi1 up to xi m of some real or complex numbers x1 up to xm. Of course, you see I hesitate to say given real numbers, because how would a real number be given if it's really a strange number that is only determined by all its entire decimal expansion that is infinite? I can't assume this to be given, but I can assume that we have approximation to a certain finite accuracy, and the task is to find integers e1 up to em such that e1 x1 plus emxm is 0. So this generalizes the thing here, because you see that in order to find a numerator and a denominator, that's the same as saying I want to find an integer relation between 1 and xi. Now you can do this with several xi's as well. So in this case you would say, okay, let's take here xi1 and xi2 and so on as generators up to xi_m, and take this lattice and attach unit vectors below like before, and then you will have that the E1 up to EM will show up here. It will be an element of this lattice if on the top coordinate you put this expression. Okay, so but with xi's instead of x's. So E1 xi1 plus 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 EM xi_m. Okay. And now LLL doesn't know that this is the vector that you want, unless we tell it to prefer this one over these ones. And in order to do this, we use again the same trick with this W. So we attach here a W, and that makes these vectors long, and it also introduces the W here. But this here, this is epsilon. This is the rounding that you get if you take here the xi's instead of the x's. Oh, but then you don't get exactly 0, but you surely get something that is small. And something small multiplied with something big is something reasonable size, so it doesn't mess up the size of this vector. So this is small, and this is long, and so we are in business. Okay. So as I said, this is then used to find relations between sums, infinite series. Usually they are not rational, but maybe you find a relation that this sum is equal to a certain simple linear combination of some other sums, and then that would be already interesting in experimental mathematics and in number theory, analytic number theory perhaps. A particular application of this one, to continue here, is to find minimal polynomials of algebraic numbers. So the task is, given an algebraic number alpha, let's say it's in C, find P in Qx not 0, for which P of alpha is 0, so that alpha is the root of it. So what does it mean given an algebraic number? Okay, so now I wrote something that I before avoided to write. I'm saying here given a complex number, but of course it's an algebraic number. An algebraic number I can specify exactly in terms of a minimal polynomial, but here I assume that the minimal polynomial is not known for the alpha. So I assume that alpha is given as approximation. And I want to recover from the approximate value of alpha as a complex number the coefficients of p. P doesn't necessarily have to be the smallest polynomial. I'm already happy if I find some polynomial that throws the alpha to 0. So how would I do this? Well, that's exactly the same problem as before. For a specific choice of xi's, you just take the powers of alpha as xi's. So this is the same as finding an integer relation between 1 alpha squared, and while you have to choose some degree, and you guess this degree, you try a certain degree. If it doesn't work, you try another one, and until you either find something or you are not interested anymore. or you start to suspect that the alpha is not actually algebraic. So let's try this here, alpha. Well, let's take a simple algebraic number. So square root of 2 is a very simple one. But you know from an algebra course, hopefully, that the sum of algebraic numbers is also algebraic. So let's take square root of 2 plus square root of 3. So we know the minimal polynomials of square root of 2 and square root of 3, but maybe it's not. Maybe we forgot how to determine from this the minimal polynomial of the sum of those. Okay, but now let's do this with LLL. So how would we do this? We would say 1 alpha, alpha squared, alpha cubed, maybe, and put this again to a high power and round it, and then append this to an identity matrix. And in this case with 4 components, transpose. And here's what the initial lattice looks like. So let's throw lattice reduce on it, and you see that we get nothing. How do you see that we get nothing? It's because the vectors are roughly of the same size, and what I'm hoping for is to get an output in which the first vector is significantly shorter than the other vectors, or maybe the first few vectors are significantly shorter than the other ones. Here all of them are somehow short, and that's because I've entered here 6 digits of accuracy only for all the powers, but this accuracy is distributed over more coefficients. Before it was just numerator and denominator, but now I have 4 coefficients, so maybe that's not enough. Okay, but let's increase the accuracy here, and you see that doesn't help, and I'm not sure what you expect for the minimal polynomial, but probably you wouldn't expect for such simple numbers that the minimal polynomial has such big coefficients. So something is wrong here. And what is wrong is the choice of d. I've guessed that alpha has an annihilating polynomial of degree 3, and it just doesn't. You have to go a bit higher with the degree and add another power to it. And then also another thing here. And then you see, whoa, this is much shorter than this one's. So it seems that we have found something. What did we find? We have found 1 plus 0x minus 10x squared plus 0x cubed plus x to the 3. And in this case, we can actually, so this is just a conjecture at this moment, but a very convincing one, because this is so much smaller than the others. But here we can actually prove that this is true, because we have the alpha in some form, in some symbolic form, that we can plug into this polynomial and expand, and you get 0 symbolically. And this proves that this is really an annihilating polynomial. It doesn't prove that it's the shortest one, but it's one that certainly works. Okay, so what else can we do? The reason we are discussing LLL is because it will be helpful for us when we in the next videos and for the remainder of this course talk about polynomial factorization. This is also the context in which lattice reduction was first proposed. And here we are actually not very far from polynomial factorization already by talking about minimal polynomials. So let's see the idea. How can we factor polynomials with coefficients in Q? Yeah, the idea is, let's do it right away here. So let's say we have a polynomial that contains this polynomial here as a factor, and maybe something else, 5 plus x squared minus 3x cubed. Expand. Okay, so this polynomial has 2 factors, assuming that they are, not maybe more if they can be split further, so which is unlikely, but I didn't check. So anyway, let's suppose we are given this polynomial and the task is to factor it. What you can do is you can compute numerically the roots of the polynomial. So n solve 0 per x, so 23, so And then you get a bunch of roots, some of which are complex and some of which are real. But you know that if the polynomial is square-free, which we can arrange by algorithms we discussed earlier in this course, then you know that every root is the root of exactly one of the factors. So that means if we have a root, let's take this one for example, and we find an annihilating polynomial of it, then this annihilating polynomial, if it has, so we would search for an annihilating polynomial whose degree is less than 7, because otherwise we already have a polynomial of degree 7. So let's search for one of degree 6. If we find one, then taking the GCD of that polynomial with this polynomial should give us a factor. Okay, so this is the idea. And we can do this very efficiently because approximating the roots to high accuracy, that's not a big deal. It's something we can easily do. And then we can take advantage of the speed of LLL, because LLL is also very fast in giving us the coefficients of a 6-degree polynomial that has a root that is very close to this root. We wouldn't here do this with 6 digits of accuracy, but maybe with 50 digits or 100 digits, and we will still get the result rather quickly. And the problem with this approach is that what is missing is what if the polynomial is irreducible? So if there is a factor, then by doing this with sufficiently high accuracy, I'm guaranteed by LLL that it will find the factor. But what if it doesn't have a factor? So in this case, I would need some estimates on how far I would have to go with the accuracy in order to ensure that if I stop here, then there's nothing lost because there's nothing to be found. And these estimates are a little bit cumbersome to do if you do this with numerical approximations. And that's why we later will play this game that I've just briefly sketched here in a slightly different algebraic context. But it's good to have this idea here in mind, because what we will be doing later is very similar in spirit to this calculation and this approach that I've just shown you here. But that's still not all. So you can do a lot of further things with LLL, and let's have a look at some more. Integer null space. So what is this? Here you are given a matrix, let's say with integer entries and n rows and m columns, and the task is to find its kernel over the integers. So that's a submodule of set to the m, and the task is to find the basis of this submodule. So you know, if you're doing this over the field, you would solve this problem with Gaussian elimination. And maybe you already know how to solve this problem over the integers. If you've heard about Hermite normal form, which which I'm covering in my linear algebra class, but if you haven't seen that because you come from somewhere else, no problem. But there is an algorithm for doing this. And we assume now we forgot about this algorithm and don't want to look it up. Instead, we want to solve this problem with LLL. So how can we do this? So how can we say I want to find all x such that ax is equal to 0? A is given and x is what we want. And the idea is the same as before. The approach is always the same. You want to construct a lattice where what you know is big and what you don't know is small. So what I know is the A, and the A has certain integer entries that have a certain size. And the x's, let's say the basis vectors of this kernel, they also have a certain size. And these are things that I cannot change, except that I can again scale up the A. If I multiply this equation here with a W of my choice, then I do not change anything about the kernel. this W does not affect the solutions X. So the solutions X have a certain size. Maybe they are big, but have a certain size. And I can ensure by choosing a sufficiently large W that the entries of A are larger than the entries of the basis of the kernel that we are looking for. And so we are in business. What we know is large and what we want to know is small. So here is the lattice. Let's say A has columns A1 up to AN. So what I do is I take here A1 AM multiplied by W and then attach unit vectors to it, similar as before. It's always the same game. And then this will contain 0 x for every x in the kernel, in the integer kernel of A. Okay, so this is small. Here you see this is a bit different from before because here we don't have an epsilon. The epsilon, we are doing throughout exact computation, so here we get really exactly 0, so this is certainly small compared to this, and this is long, if W is chosen sufficiently large. So let's try. Let's take a matrix A, table random integer 10 to the 10 maybe. Let's take 5 rows and 7 columns. Is this big? No. Okay. Now let's see what I said here. What do I need to do? I have to attach the identity matrix at the bottom of the matrix. Okay. So this means I have to transpose A, join identity matrix 7 and then transpose again. Is that it? No. Okay, so I have to I don't transpose it without transposing. This looks good. So this is 1, 2, 3, 4, 5. Yeah, this looks good. Okay, so this is the first. Right, this is the first column of A, but here written as a row because Mathematica thinks of generators as rows. And then this is the second column with the second unit vector attached and so on. So let's do lattice reduce, and we see nothing. So what we were looking for, or what we were expecting, is vectors that have zeros in the first 5 components, and none of these vectors has this. But we should not conclude from here that the kernel is empty. In fact, it cannot be empty because I had 5 rows and 7 columns, so there should be in the if you think of vector space, there should be a 2-dimensional solution set, and this solution set will also have some integer components, some vectors with only integer components, so it can't be this. What we forgot was this W. So we have to enter a W, and it's not so clear. You can work out how big it should be depending or knowing the size of the entries of A. But today I don't want this. I don't want to think so much about this. I'll just choose something that is sufficiently large, or that is so large that I'm confident that I get the right result. And then here we go. So let's see what we get now. Here you see a big difference. Here, this is the third vector. The third vector contains something. Every non-zero vector here at this point will contain every every entry in the top n rows will be a multiple of w, and unless it's 0, it means it's a very big number. So this is what we observe here. This is a multiple of w, and since the w is so large and LLL worked very hard to get small things, it just w itself. So LLL wasn't happy with even giving us 2 times w, because it wants to make that small. And here it succeeded in making it even smaller by eliminating these bad expensive components altogether. So here we get 5 zeros, and that means that the remaining vectors are elements of the kernel. And since there are 2 of them and they are linearly independent, we can conclude that this is actually a basis of the kernel. Yes, assuming that we are in the generic case and A has a 2-dimensional solution space, which it will have because it's a random matrix. So here, this is not just a vector space basis of the solution, but it's a basis of the integer kernel. Okay, so this is another application, and I have one more, maybe 2 more, maybe 3 more. Let's see. If you're stranded on a lonely island and you have access to a very weird computer algebra system that doesn't have an implementation of the Euclidean algorithm, but it does have LLL on it, then you can compute GCDs. So, and actually you can also compute cofactors. So you can emulate the extended Euclidean algorithm with LLL. And so the task is, given a and b integers, find g, s, and t such that g is equal to the GCD, the integer GCD a and b, and g is equal to sa plus tb. So a and b are given, and s and t and g is what we want. How would we do this with LLL? It's always the same. You make you come up with a lattice where what you know is large and what you want to know is small. So here's how you can do this. Actually, it's not much different. Actually, this is somehow again a variation of the thing that you had before. So here you can view this also as a system of equations, where here you have one coefficient given and it has 3 variables and 1 equation. So you just solve this system over the integers, but you have to do one more thing, and the one more thing is you don't want to have a solution in which the size of the components are balanced. Instead, you want this to be as large as possible. Right? So you want to get the greatest common divisor. I hesitated a bit because now we're doing it differently, but we look at A and B and all the linear combinations that you want to get. So you want to say A 1 0 and B 0 1 for any choice of S and T. This will contain the vector that has here S and T, and here it has SA plus TB. Okay, now what we want is that among all the, so the G is supposed to be the GCD, so among all the divisors, the common divisors of A and B, we are looking for the greatest divisor. But we don't really have a key to accessing divisibility or express divisibility in terms of LLL. Instead, we turn this a bit upside down and say among all the linear combinations, the integer linear combinations of A and B, we are searching one that has the smallest value. So that's the same. So you can think about this. This is the same. Oh, so we want this to be small. How can we make this small? We are attaching a weight to it so that LLL knows this is what it has to work on. This is what it has to make small, because that's what determines the size of the vector, and the rest is just a secondary interest. So you put a W here and a W here and a W here. And then you get W times G for a G that is like this. And if you put the W very high, then GCD will try very hard to make the G very small. And the smallest G that you find in this way, that will be the GCD. Okay, so of course you get here W times the GCD, but you divide out W and then you have the GCD. So let's see if this works. Let's take some number A and some other number B. So see, they don't have a GCD probably. Okay. So let's give them a GCD. So maybe like this. So here are the two numbers. What I do is now I say identity matrix 2, append this, and transpose lattice reduce. And don't forget the W, so let's take 10 to the 50 to be on the safe side. And here's what you get. First, you get a vector that has 0 in the top coordinate. No, sorry. What is here in the handwritten notes on the top is here in Mathematica at the end. And this is S and T. So these are S and T that linearly combine A and B to 0. So remember from the Euclidean algorithm, the Euclidean algorithm terminates when the candidate greatest common divisor becomes 0. So this is the 0 that you see here. This is the step one step ahead of the termination. And here, this is the previous one. This is the this is the smallest thing that LLL can achieve in this coordinate. That's 0. But the second smallest thing is just the GCD times 10 to the 50. So let's take here minus 1 divided by 10 to the 50. Minus 1 picks out this number. And this should be the number that I've introduced here as a GCD. It is up to sign. Okay, the sign doesn't matter. And in addition, you get the cofactors, because if you take here, this here times A plus this here times B, then that's again the GCD. So this is how you do extended GCD, the extended Euclidean algorithm with LLN. Okay, what else can you do? You can do rational reconstruction. This is something we discussed in the context of evaluation and interpolation. When you have a homomorphic image of a rational number, then the question is, what is the pre-image? And that's not a meaningful question because there are lots of pre-images. But what you're interested in is a pre-image in which the combined size of numerator and denominator is roughly equal, so small. And small is again the keyword that says, oh, that's something we can probably do with LLL, and this is right. So here's a task. Given A and M integers, find P and Q, also integers, such that P divided by Q is equivalent mod M to A. And they should be small. That's a bit in spirit. This is a little bit similar to Diophantine approximation, the first application we discussed today, except that In Diophantine approximation, you have as input a numerical approximation of a certain number, and you want to reconstruct what number was that, what rational number has led to this approximation. And here we have a homomorphic image, but a homomorphic image is also some kind of approximation in a very abstract sense, not in terms of any Euclidean distance or so, but it's also an approximation in the sense that it contains some of the information of the original fraction, and some part of the information was discarded. So you can go from here to there easily, but going back is magic. And now we are doing the magic. Actually, it's not so magic after all, because maybe it starts to get boring already, because I'm telling you always the same trick. Here, what you would do is take this equation and rewrite it differently. So what this means G is equivalent to M mod M to Q times A, and this you can also write as P is equal to Q times A plus R times M. And this is an equation where you know the 1, you know the A, you know the M, and you want to know, actually you don't care about the R, but okay, we get it for free in addition. You care about this one and you care about this one. So how would you build the lattice? Here's how. You could say this is again a very simple linear system that you want to solve over the integers. So let's just solve it the way we solved it above for an arbitrary matrix. We would say 1 on, so let's write this as -1 plus equals 0, and then this is -1, 1, 0, and then A 0, 1, and then M 0, 0. I could have put an additional coordinate here to catch the R, but I said I'm not interested in the R, so I didn't even include it here. And this lattice will contain the P, Q, and 0 here for every reasonable choice of P and Q. So actually for every integer choice, for every choice of integers P and Q that satisfy this equation, this vector will be in this lattice. And LLL will find among all of them one that is short. You can simplify this a little bit because this vector here is really very explicit. So you can also say you take, or L is equal to, let's take just A1 and M0. Well, then what would this be? This would, if you think of taking the first vector and multiplying it by Q, then you would here have Q times A, but Q times A is equivalent to P mod M, and I can add here suitable multiples of M to the first coordinate without changing the second coordinate. So this here would just contain P and Q without this 0. So this should also work. Let's see if it does. So let's take maybe a polynomial mod, some number, okay, let's first take the number. Okay, this is the number, and now, or maybe that's a bit too much. Let's take something smaller. 17 by 30, did we have 23 in the beginning? Okay, let's take this one, and let's take a more reasonable prime. Polynomial mod 38 and 1091. This is the A, and then 902 is the A, and 1091 is the M. And what I just said was I take 902 1 and 1091 almost 0, and I apply lattice reduce, and whoop, 17/23. And here I was very lucky because that one is not much longer than this. Yeah, but that's also not surprising, because if you take the product of those two, then you actually get very close to this prime. If you want to have a more dramatic effect, then you have to choose a bigger prime. What would be a bigger prime? Maybe 2 to the 31 minus 1. That's a good prime. And then you have this A, 41, 2 to the 31 minus 1. Here, and you see this doesn't change, but this gets bigger, so that's an indication you found something reasonable. Okay, so I hope you are convinced that LLL is a really useful tool. If not, then I have one more. Let's generalize this a little bit further. 8. And let's do algebraic reconstruction. So this is a bit like the thing we had earlier, where we tried to reconstruct a minimal polynomial or an annihilating polynomial from a homomorphic, not from a homomorphic image, but from an approximation. And here this is a variation of this idea, but in an algebraic setting. I assume I have given an algebraic number field where alpha is algebraic. So that means this is Q x mod m, some m irreducible polynomial over x. So, and I have a map phi. Okay, so let me write this, but it doesn't really make sense, but let me write it nevertheless. From Q alpha to set P. That sets alpha to root of m in set P, assuming there is one. And it sets otherwise a rational number to its homomorphic image. If denominator is coprime with P, and otherwise I just leave it undefined, so it's a partial function. Okay, so you can so this is somehow an extension of the idea of going from rational numbers into a finite field. We go from rational numbers into a finite field. That's what we discussed in the lecture about evaluation and interpolation and about the computation with homomorphic images. Now I want to go from an algebraic number field into a finite field. And this is how to go into the field, and the question is how do we come back. So the given, so this is actually not the given, this is the setting in which everything takes place. And now is given is some A in set P, and the question is find an element of the algebraic number field that is the pre-image of this A. Find a pre-image of A in Q alpha. And again, this is a slightly informal because it's easy to find a pre-image, because if you just take A and view it as an integer, then its image mod P would be A. and a as an integer would certainly be contained in here. But I'm thinking of a as a number with lots of digits, and the question is, can I find here an element that has fewer digits, smaller coefficients? So what do these elements look like? So the elements here, they all look like this. So you know that algebraic number field is defined like this by an irreducible polynomial, but it's also a vector space which is generated by the powers of alpha up to the degree of m. So all the elements of this field look like this: u0 plus u1 alpha plus u2 alpha squared plus ud minus 1 alpha d minus 1 for certain u's that are in Q. Sorry. They all look like this. Now I don't like it now that the u's are rational, so let's make them integers and pull out common denominator, put them over a common denominator, so and then I can say for certain u0, u1 up to ud minus 1 and v that are integers. And what we want is a pre-image of a where these numbers are small. And you do this again by constructing a lattice in which what you know is long and what you don't know and what you want to know is short. So let's see, how would we do this? So let alpha bar be phi of alpha. It's the image of alpha in set P, and consider the following lattice L. Yeah. So what do I want to say now? I want to say that I can get for every term here in this representation, I can get an immediate answer, which is a bit like saying just take A itself as an answer. I could also say take A over alpha times alpha, so maybe alpha bar here, compute this in set P, and this times alpha, then phi of this would also be A. And actually this works also for powers of I, for powers of alpha. So if I so what I mean here is I take the A, divide it in the finite field by this, do the division there, but then view it as an integer and multiply it by this. So then this whole thing here would be in Q alpha, and then phi applied to it would be A. So this is computed in this, but then interpreted in a set. Okay. So this gives me a bunch of generators, because I could just say here, okay, take A, 0, 0, 0, and 1. This is the component that will, in the end, catch the denominator. Or you take 0, A over alpha bar, 0, 0, 0, 0, 1, and so on. Or you take 0, 0, 0, A over alpha bar to the d minus 1, 1. So, and then this will be a lattice that contains u0, u1 up to ud minus 1 and v. or yeah, or to say every vector in this lattice would give rise to a pre-image here, because the pre-images here are so all these are somehow the canonical pre-images, and I can combine them to other pre-images. This is what the lattice does, and then what LLL does is it finds you one in which the coefficients are small, because this is maybe the one that you're looking for. Okay, so these were now 8 applications of LLL, and there are many further ones. But maybe these 8 ones are enough. And let us now turn to polynomial factorization. So this is now really entering into the third part of the course, and it's also actually the final part. For the rest of the semester, we'll be talking about polynomial factorization. So the task is this: you're given a monic polynomial over a field, and you know that polynomials over a field form a unique factorization domain. You can break f into irreducibles, but the usual argument that you are giving in a basic education in your studies is not a constructive argument. It just says there exists a decomposition of f as a product of irreducible polynomials, and it is unique, but it doesn't tell you how to find it. So our task now is how to find it. We will assume the f is monic typically, and we can then assume also that the irreducible factors are monic, because the multiplicative constant factor doesn't contribute anything to the problem if K is a field. And we can also eliminate the exponents, so we can say that the p's are pairwise distinct if we allow exponents, and we can discard the exponents and still keep the assumption that the p's are pairwise distinct if we assume that the f is square free. And we can assume this without charge, because we know how to compute the square free decomposition of f. So if we are given an arbitrary polynomial, we would first do as a preprocessor a square free decomposition, and then apply factorization to each of the components of the square free decomposition. These components are square free, so they qualify here for an f to which we apply the techniques that we will discuss in the sequel. Okay, so there's a fundamental difference between polynomial factorization and polynomial arithmetic, as we discussed in the first and the second part of the course. And the difference is that the ground field matters. So here's an illustration of this that maybe serves as a warning, and that you hopefully keep in mind. If you are given this f and ask what is the factorization of this f. Now if I write it like this and I don't specify what k is, well then I don't know what 2 and 5 and 4 are, but I know what 1 is, because every field contains a 1. And when I say 2, when I write 2, then I mean 1 plus 1, whatever this is in the field, and 4 and 5 accordingly. So this is something that I can write down in every field. But the answer to the question what the factorization of f is still depends on what this field is. So you could, for example, choose set 3, and then you see that in this case f is not even square free. It's a square of another polynomial. If, however, you take a field with 5 elements, then it's a different story. Then it is a square free, but it's not irreducible. So it breaks into 2 factors that are irreducible. And if you take a different modulus, well, then it breaks even further. So here, these 2 polynomials over set 5 are irreducible. And we will see how to check this. Actually, here it's easy to check this, because they're just If it's not irreducible, it would have to have a root, and there are just 5 candidates, so you can check it for every choice of x. This one doesn't evaluate to 0, so this doesn't break further, and this one also not. But mod 13, it factors completely. So you could also factor this over q, and over q it is irreducible. And we will have to discuss how to recognize this, how to recognize this efficiently. Factorization over Q, this is what happens if you go into a computer algebra system like Maple or Mathematica, and you just enter an expression like this, and you say factor. Then by default, it would factor over Q. Now, unless you have, so if you really have just integers as coefficients, it would factor the polynomial over Q. If you want to get a factorization in one of these fields, you would have to specify additional options for the factorization command, because how would it guess otherwise that you are working over this field? That's different in Sage, for example, because in Sage every polynomial is not just an expression, but it's an element of a certain ring. So if you write something like this in Sage, then Sage would know whether you mean a polynomial over this field, or whatever other field. And then if you say factor, then it factors in this field, that is the coefficient field of the polynomial in which the f lives. But that's just a difference in the user interface. It doesn't make any difference in the mathematics. Now we can factor the polynomial in other fields, for example in an algebraic extension of k. So if you take q adjoint square root of 2, then it turns out that the polynomial is still irreducible. You may ask, why would it not be irreducible? And the answer is, well, because it might factor for some other choice. So here's another choice. If you take square root of 3, then this polynomial factors over this field because you can write it like this. So here there's a factorization where then, of course, the factor would somehow have to involve the square root of 3 because there's no factorization over q. But the statement here in the previous line says that there's no such factorization like here that you can form with using square root of 2 instead of square root of 3. And how do you recognize this? How do you see this? This will be a question that we will have to discuss. You can also discuss, here's another one. The I is mathematically not much different from square root of 3. It's just a quadratic extension of q, and it turns out that in this extension the polynomial here also factors into 2 quadratic factors. And you see also that there's no apparent relation between this factorization and this factorization. That's because there's no apparent relation between square root of 3 and I. So this is really just a completely different story. And in fact, it would be fair to say that the f is a completely different polynomial depending on whether k is this or this. So you see it has a completely different factorization, and it may even have a different number of factors. You can also factor over the reals. If you do this, then you get essentially this factorization here, because this here, it's then a real number, but 2 plus square root of 3 is also a real number. So if you embed this field here, then it could have been that this splits further, but it turns out in this case it doesn't, and that's related to the polynomial having a factorization in this field. So things are not completely unrelated, but it's also not clear immediately how they are related to one another. And you can also, of course, do a factorization over C, and you know that C is algebraically closed. And so if the polynomial is square-free, then factoring over C is in fact the same as just finding the roots. The factors have complex coefficients, and they would, you cannot write them down explicitly in general, but you maybe want to write them down as an approximate as approximate coefficients. Also here in the reals, it's a certain algebraic number. But if you think of it as a real number, maybe you don't want to think of algebraic numbers. You want to just think of real numbers, and then, well, then it's just a number. All right. So the difference between polynomial arithmetic and polynomial factorization is that in polynomial arithmetic we can think of an arbitrary k. Maybe sometimes we have to distinguish between characteristic 0 and characteristic non-zero, but at the end of the day, the goal there can typically be achieved, that you have an algorithm that works for arbitrary ground field k. And this is something that we can not achieve in polynomial factorization, because as you see on this slide, the output differs depending on what k you have. So also the algorithms must necessarily differ from one k to another. So we will have not just one factorization algorithm that works for any field. It's impossible to have in view of this phenomenon here. Instead, we will have a zoo of algorithms. Okay, and the rest of the course will keep us busy with going through this zoo. So let me give you an overview. Here is what we will discuss and discover. Of course, we cannot handle every field. There are just too many choices for this k, but we can handle the most important ones. And we have already said that factorization over C is just the same as root finding, and factorization over R is closely related to factorization over C, is almost the same as root finding. Root finding, finding approximate roots of exactly given polynomials to a very high position, is a very interesting topic. On the boundary between computer algebra and numerical computation, but it's not the topic that we want to focus on in this course. So let's just say that this is a numerical procedure by which you can do this and estimate how close is your root, at which point will you have which accuracy, and so on. So that would be factorization here. But let us focus on the other ones. So we will these algorithms will be based on each other. So we will next time in the next video start with talking about polynomial factorization over a finite field. And then I want to go to this thing where there is a ring that I have to first define what it is. So this is an intermediate procedure, factorization over this ring, before we then go to rational factorization, where I said this is the default question that is answered when you ask for a factorization in a computer algebra system. And from here we will then go to factorization over algebraic extensions. And here on the side there's something that we will discuss in between, which I think will be helpful for understanding these two edges and also clarifying what this is. Here the idea is that that we will say, okay, let's assume there is some field for which I know how to factor polynomials over this field. Then how could I turn such an algorithm, or extend such an algorithm, into an algorithm that factors polynomials over the rational function field over k? So here t being a transcendental variable. So this is also a field, and I want to have an algorithm that factors here, assuming I have an algorithm that factors here. And one way of doing this is to go through an intermediate stage where you construct an algorithm that factors polynomials whose coefficients are formal Laurent series rather than rational functions. Okay, and this here will then be something analogous to a Laurent series for numbers. So then this will be this will be a helpful intermediate step on the way from going from finite fields to rational numbers. Rational numbers corresponds to rational functions. Finite field corresponds to any field. And this funny thing here, what we will discuss more closely in a later video, will then be analogous in this analogy to Laurent series over this field. Okay, so let's stop here for the moment. What we will continue with next time is factorization of polynomials over a finite field. So that's all for today. Thanks for watching, and see you next time.